power is the rate at which you do work. So if you've got a more powerful elevator motor, right? If you've got a more powerful motor on your elevator, then it's going to lift your elevator faster, right? If you've got a more powerful car, then it's going to speed your car up more quickly, right? So that's the notion here, and it's a very simple formula. The rest of the world has this formula here, which is power is work divided by time. Now, sadly, that does not appear in the IB data packet, right? All they give us is force times velocity, which is derivative and weird, okay? So you've got to memorize this thing, right? So this is work divided by time, right? So that's work in joules, time in seconds, right? And then this is power, okay? This thing here is easy to derive. It's just kind of a weird way to write power, right? If I derive it, I do this. Power is work divided by time, so it's force times distance. I'm just substituting work is force times distance over time. And then, of course, distance divided by time is velocity, right? Right, so that's force times velocity, okay? So that's basically how this formula works, is it's just a rate problem. You can even make little triangles like this, like work and power and time. These are really pretty simple, right? Cover up the thing you want. If you want power, cover it up. It's work divided by time. If you want time, it's work divided by power, and work is, of course, power times time, right? So these are really pretty simple relationships. Let me just do some examples here, okay? There we go. Okay, a person does 48 joules of work in 6 seconds of time, right? What's their power output? Well, power is work divided by time, so it's 48 joules over 6 seconds, right? Well, without even using a calculator, I can get that that's 8.0 joules per second. Now, watt is another way to write joules per second. Watt is another way to write joules per second. Watt, I don't hear you laughing. So usually you laugh at that joke, right? So it's a capital W, it's somebody's name, right? Okay. So let's do a problem worthy of, being an IB physics student. Okay, so here we go, right? My son and I climbed from the Cold Springs campground on Mount Adams' summit. We started at 7, got to the top at 11. So if you're paying attention there, the time is 6 hours, right? I have a mass of 75 kilograms. I was carrying an 18-kilogram pack with skis, probably at least, right? Okay, that was a heavy pack. And so my mass is going to be the sum of those, right? And then what was my average power output if the elevation gain is 2,030 meters, right? Apparently the answer is 86 watts 2 times, right? Somewhat surprisingly. So what I'm going to do here is, let's first figure out what the time is. The time is 6 hours times 3,600 seconds for an hour. Right, so that is 6 times 3,600. I got to turn my calculator on. What's that called when you type numbers into a calculator that's not on? 21,600 seconds. Okay, so we got the time. Okay, and then power is going to be work divided by time. The work I did is just going to be the potential energy. So this is one of the things about this, is that work is not just work. It's any change in energy, any transformation of energy you can stick in there, right? So it could be any, and we're going to spend more time on this, right? Okay, so in this case, the work I did is my MGH, my potential energy, right? So that's going to be 75 plus 18 times 9.81 times all the elevation gain, right? Divided by 21,600, right? So that is 75 plus 18 times 9.81 times 2,030, okay, divided by 21,600 seconds, and that gives us 25.74 watts, which is actually quite a bit of power because I don't know if you ever played with that thing at OMSI where you get to pedal a bike and light the lights up, but lighting up a 100-watt light bulb is actually a fair amount of work. But so with 2 sig figs, we'd round it to 86. Okay, and then our final example here is we have to have equal time for our force times velocity, right? Okay, so this is the power, right? I'm going to use power is force times velocity, and then we want to find the force, so therefore force will be power divided by velocity. You can make a little triangle out of these guys, right? Power is force times velocity, right? So force will be power divided by velocity. So anyway, but the power, I've got to figure out the power. The power is going to be 30 horsepower. This is what a horsepower is in watts. So that's the conversion factor. Okay, and I don't know that a horse can actually put out that much power. What's interesting though is that a bicycle racer like Lance Armstrong can actually put out more power than a horsepower for periods of time, which is somewhat amazing. Okay, so anyway, our power is 30 times 745.7. Okay, so let's do that. 30 times 745.7 is 22,371. 22,071 watts, right? And now we're all set. We can go power, which is 22,371 divided by the velocity, which is 25 meters per second, right? Right, and that's watts. Apparently a watt divided by a meter per second is a newton. It's a newton. Okay, so divided by 25, and you get 894.84 newtons. With 2 sig figs, you'd have to write that.